Okay, good afternoon, everybody. I hope you have enjoyed the lunch break. And if our online participants are already there, we can start the afternoon session with a talk from Patricia. As usual, you will have a very nice talk about the characterization of and maybe a wrap-up of the project results. So the floor is yours.
Is this working? Yeah. How do I start? Oh, it is. So I come from SINTEF, which is in Norway, a research institution. And the role of SINTEF in START was to characterize the materials and organize the characterization of the other partners. So that's what I'm going to talk about. So here you can see just a very small diagram showing that in work package 4, which was materials characterization, we were handling and also helping with work package 2 characterization, although you were quite independent. With work package 3, which was the materials processing, and then also with work package 5, which is the device production. So I'm going to present some results, of course not all, but the main conclusions. One of the deliverables we had in task 4.1 was to create a mineral database with all the minerals which have been investigated in the project. From this database, we selected the minerals which had the most amount of tetrahedrite. There were minerals from Slovakia, from Spain, and from Germany, which had interesting features. The ones from Germany were not accessible, because in Germany we didn't have access to the minerals. It was very restricted. So it was mostly from collections. And the ones from Spain were a little bit worse in terms of tetrahedrite proportion than the ones from Slovakia. So we focused on the ones from Slovakia. So we have this database, which is now only accessible to people in the project, but that we are considering to make it free and accessible in Zenodo for everybody. One important aspect was the amount of iron that the minerals contained, because as you will see later, iron is problematic for tetrahedrites. Although there's some synergy with other elements, but I'll explain it later. And the amount of iron can be quite high, depending on the minerals. But the ones from Slovakia had around, it varied, depending also whether the mineral was concentrated or not. But it ranges 4, 5, 7 is what we had in the samples that were given to us. So when we talk about tetrahedrite, it's important to discuss the structure. The structure is quite complex. And when you look at it like this, with a conventional unit cell, in fact, you have 2 formula units. And traditionally, the doping of this structure is done by replacing copper, by substituting copper. But it is interesting because you have 12 copper, but they are not in the same copper atoms, but they are not in one Wyckoff position. There are 2 positions, 2 crystallographic positions. And one is connected to, does this work? Oh, very, very little. No, yeah. So you have this one in which the copper is connected to one type of sulfur atoms. In some sort of a tetragonal coordination, and then you have this trigonal planar coordination. what we want to do, what the system allows you to do, is to replace the copper in the green figures. These ones are very important because these copper atoms, they rattle between these two electrons, which are associated, they are inner electrons of antimony, and they somehow have some repulsive influence on copper, and so the copper atom rattles in this position. And by doing that, it disperses phonons, which are the ones that carry heat. And that's why the thermal conductivity of tetrahedrite is very low. And this is very important because the mean free path of these phonons, which are dispersed and which are responsible for the very low thermal conductivity, they do so, the mean free path is at atomic level. This means that if you have grain boundaries, porosity, nanoprecipitates, none of it is good for tetrahedrites. Because what you need to, everything happens at atomic scale, so all the microstructural heterogeneities are bad for the thermoelectric properties. So we want to replace this. We don't want to replace this. The structure doesn't allow you to replace this. It only allows you to replace that. And even so, only about 2, because 2 atoms of this 6 copper. Because this copper is monovalent, so plus, and when you replace with other atoms, like nickel or iron, it's 2 plus. So you can't replace, there's a charge imbalance that the structure doesn't allow you to replace a lot of those coppers. Typically, the maximum is 2 atoms. So this is what we want to do. We want to replace a type of atom, of copper atom. But if you go to the literature, so the problem with us, we knew we had to use iron because iron exists in the mineral. But should we use something else? How much should we use? Should we combine? What concentration? So if you go to the literature, as we did to try to find out, it's a very big mess. First of all, people, of course, report at different temperatures. They don't allow for the temperature dependence. And you don't really, these are the best values, but it's very confusing. You don't really take any information out of it. So the first thing we decided to do was to create an analysis of all these studies, which is called a meta-analysis. This was done by a master student who stayed with us at SINTEF. So she went to the literature, got all the papers that she could on tetrahedrites, collected all the points. There is this very important database. I don't know if you know about it, but it's a database created by a Japanese team that gets all, they try to publish put it in a database, all the papers with thermoelectric data, but they only had 20 papers on tetrahedrites. But at the time, like last year, there were 58 papers. So we decided, okay, we're not going to use this database, you're going to do it ourselves. So the student tried to use automatic collection of the papers, so feeding to artificial intelligence models, feeding the figures and trying to extract the points. It turned out that she could only do it in half of the plots, because if you had this type of things, then the AI got confused. Now the tools are much better. So what my colleagues tell me is that now, if we would do it now, 1 year later, we probably would get much better results. But at the time, she could only extract 50% of the data, and then the rest she had to do by hand. She used also some assistance, but basically you have to indicate where the points are. So when she does this, then we try to plot it, to try to see what kind of temperature dependence we get. And what you see is that it's a big mess. So at each temperature, you get very high values and very low values. 0 values are common, even at a high temperature for tetrahedrites. So this is all the tetrahedrites combined. No doping is considered. This difference between the dopants is considered here. Also because we don't have so much points. But for the undoped, we had almost 400 points, so we could also do it. The same type of plot. And you see here the lot of zeros. And you see that the distribution is skewed towards low values. So it's not a normal distribution. So clearly we have a problem of there is a lot of things going on here, and it doesn't seem to be related to doping, because this is the undoped material, you see the same. So clearly there is a problem with processing. There's something in the processing which is not, it's giving you a huge dispersion of results, and this seems to be true also for other materials. But then we try to see, okay, can we relate the sintering method and the sintering temperature with the performance? And if you see here, so this is for all the samples, the ones that were produced by hot press, which is clearly the most used technique, SPS and other techniques. It is very interesting because what you see is that the ZT value, again, no difference between dopants. This is all tetrahedrites. And what you see is that the ZT is very similar in all of them. So clearly, the processing method isn't important. It results in the same ZT and in the same dispersion. Then we try to see, okay, what happens with the sintering temperature? So we again plotted all the results we had for the full data set, only fixing the temperature, 350, because 350 was the temperature we decided in this project that the material should be used because of the melting temperature of tetrahedrite not being very high. And these stars, these are the average values with the dispersions. This is the one standard deviation, and then the stars are the top ZT, regardless of the composition. And it's very surprising because from here to here, how can it be possible that when you sinter at 320 or you sinter at 550, you get the same result? Because this is what it tells you. It tells you that the sintering temperature is not a variable, it's not important. And that is, again, very strange. And it suggests, again, that there is something wrong with the processing. Then we thought, okay, maybe this is because it's different compositions. Different compositions need to be sintered at different temperatures. Then we go again to the undoped. We also don't see a very clear relation between temperature and sintering temperature and ZT. Of course, here we only have 52 data points. That is the problem. There's not enough material. Then, enough points. Then we try to see, okay, is there a relation between ZT and density? And of course, here there is. You see that above 95, it's quite constant and the dispersion is smaller. And then it lowers, and there's a lot of dispersion, which also makes sense. Then we try to analyze the doping effect. There are some works in which people replace antimony. There are other works in which people replace sulfur. This is much less. But most work published in the literature replace copper. So we have a plot here where this is copper, 12 is the undoped. The undoped and also the ones which are only doped here or here. And here we replace copper with something else, and here we add copper. And what you see is that clearly adding copper seems to be positive because the ZT seems to increase. But here is a huge mess. But what we have done was we tried to represent the quantiles. So, and you see that you can do it as a parabola, and here the result is what we could expect, is that if you replace a lot, you get a worse behavior. And of course, there's a maximum which is around here. It depends on the dopant, of course, and this again is for all dopants. But moderate substitution of copper is what seems to be good for ZT. Again, when you try to plot the elements now, okay, so how should we dope our material? You see again that the most common dopants, which are here, this one's here, you don't really see much of a difference. Manganese, chromium, manganese, iron, you see, that's the only significant. I'll talk about it later, but all the others, they seem to have a very similar, remember, this is the average, this is the top performing. They have very similar ZTs at 350. And when we perform some statistical analysis on this, The only one which is significant, and it's very unfortunate, is iron. And iron is always bad. And iron is always in the mineral. So that's the only significant values. The rest doesn't, if you apply the t-test, the p-values tell you that they are not significantly different. Again, when you plot the best values, we always chose to plot at 350. So you don't really have the ones that you see in the literature, because those values were obtained at higher temperatures than 350. So when you try to see for the ones which have the dopants which have the most points, and this is nickel and zinc and iron, these ones are the ones which interest the most for start, and these ones are the one, it's the dopant which has been more studied. What you see is that iron seems to have a trend, which is always bad. It's not too bad here, around here, so very low substitutions. Zinc seems to be okay until 1, and then it decreases. And nickel seems to be okay all the time. But is that really true? So when you look at the microstructure, what do we see? This is a TM image. You see a lot of pores, which I'll discuss in a while. But if you do EDS analysis, you see that nickel, even if you have one, you substitute one atom, that's about 3%, 3.5%, you see that nickel precipitates in the grain boundaries. So in fact, when we're saying that you can replace until 2 atoms of nickel, in fact, you can't, because with 1, so you're adding nickel, but nickel is not in the structure. It's precipitating, it's getting out of the structure. So you see, one of the points of this presentation is to tell you that if you don't observe the microstructure, you can't really conclude much from the data, because it can be whatever. So we also did some DFT calculations to try to understand what was going on. So what you see here you have spin up and spin down, the 2 spins. In the case of zinc, they are similar because the material is not magnetic. The zinc, nothing is magnetic in this structure. And in the other ones, you have uncompensated electrons, and then you get a difference between this side and this side. But basically, the idea is at the Fermi level, you have a lot of states. That means that you have a material which is conducting well. If you don't have a lot of states, then it's not conducting so well. You see that zinc doesn't seem to do much to the electronic structure. It's very similar. And it's still conducting. So, and this is we are replacing only 1 atom in the structure. Manganese, it's also not too bad. And then you start to modify more the structure. And what you see is that when you come to iron, the problem with iron is that you have a very low concentration here, and it's very localized here. These lines, they are not hybridized with the ones below. So when the charge carriers, they get trapped in these states and they don't move. They can't go away from here. It's very localized. I'm not a DFT person, so I'm trying to say what my colleagues told me, the ones who made this. But this weak hybridization is the reason why iron is not, because when you replace with iron, what happens is that the conductivity, the electrical conductivity becomes very low and the material becomes insulating. So it's not good for thermoelectric properties. The good thing is that when you replace iron, when you substitute copper with both iron and zinc, then you get a synergistic effect and you get still some states at the Fermi level, so the material continues to conduct and the thermal conductivity reduces. So this is what the sweet spot that we found in START. So just some results for the replacement, for the substitution of antimony or sulfur. And again, it's very similar. You see, you don't see, I mean, it's always around 0.8, and it's regardless of the atoms you're substituting. It gets always the same. So people have a lot of papers discussing the doping of tetrahedrite, but if you really perform an analysis, what you come to the conclusion is that they're all the same. If you take into account the temperature at what you're measuring, it's all the same. So, and the reason is, we believe, because the materials they are always very porous. So in this case, we didn't really make a very detailed study because we found this quite recently. I mean, the samples were always porous, but we thought it was our fault. So instead of trying to understand what was going on, we were trying to change the sintering parameters, but they were always porous. So if you sinter at 340, what you see is that you have larger pores, and they are not really so spherical. They are rounded, but they are not, you still see that they are not totally spherical. At 500 degrees C, then they are totally spherical, and they are smaller. So we think that there is, at lower temperatures, there's densification occurring, but also gas release. And then when you're really at a much higher temperature, you have a capillarity-driven pore equilibration. You see the grains are very, how do you call it in English? Equiaxed. So they look like very well crystallized. And then you have all these pores which are very small. And the reason is, if you look at the sublimation temperature of boiling temperature of sulfur, it melts at, this is pure sulfur, it melts at 116 degrees C and it boils at 445 degrees C. And of course these are compounds, but this is a good indication of the high vapor pressure in tetrahedrites. So there is a lot of gas release. These materials were confirmed to be tetrahedrite, that's what you see here. In the, this is swapped here. This is a little bit of famatinite in the undoped. So the colors are swapped here. But this might explain, this might be the reason why you always have a lot of porosity. They're a little bit different because here there's this smaller porosity, smaller pores, many, and here lower density, but not totally spheric. But this might justify why, regardless of the temperature, you get this very big dispersion and very similar results. So the question is the porosity beneficial? Because if you go to conferences on thermoelectric materials, people are always trying to get pores and nanoprecipitates and so on. Is it beneficial in the case of tetrahedrites? It shouldn't be. Because if you go into the theory of this behavior, what the theory tells you, and there are many papers about it, is that in tetrahedrites, this is the mechanism that disperses phonons. So this should not be good. This is always bad. But still, the ZT is quite high. In this case, it was sintered at 500 degrees. You see the grains are very polygonal, but it's a lot of porosity. This is TEM, this is SEM. Another sample, this is undoped. And you see again, and if you look at atomic scale, you see that the pores are much larger than the atoms. But this is a pore, it's still quite small, like 4 or 5 nanometers. So it's nanoporosity. But I doubt, and you see also some regions with low mass in the microstructure, which I don't really understand what they are. They are maybe some diffusion pathways, we are not sure. But for certain, there is a lot of porosity. But they should not be scattering phonons. But now the question is, why is this arising and what happens? So in this case, this is an iron zinc sample, synthetic. And when you look at, so again, a lot of pores, but now it seems there's something inside the pores. So if you try to analyze what's inside the pores, you see here, you see that this arrow here corresponds to this line profile, and what you see iron, and you see sulfur. So and you see oxygen. So what we have is a sulfate. And the sulfates have also, iron sulfate has a boiling point of 330 degrees C. So we are having two things here. sulfide forms, this means that whatever oxygen is in the structure, it's going to be captured by the iron and the sulfur. So you're deoxidizing the structure, which is always a problem for the materials which are produced by powder metallurgy. You always have oxygen, there's always some oxygen. This is deoxidizing the structure, but at the same time, it's creating the porosity. So, but again, the ZT is relatively high. So we don't really know why the porosity should not be beneficial, but the fact that we are deoxidizing might be a good thing. This is a sample that included mineral tetrahedrites, which were mixed and mechanically alloyed with a synthetic. And in this case, the percentage was 20% mineral, 80% synthetic. And in this case, it's again, the ZT is again good, but you look at it and it's a mess because it's full of pores and there's something inside the pores. In this case, if I recall, we have oxygen and we have iron and we have sulfur. So again, iron sulfate, which seems to be a good thing, but we have no idea why. But so you see, if you look at the numbers, if you look at the ZT and the temperature of sintering, and you don't look at anything else, there's very little you can conclude because you need to characterize the pores, you need to characterize what's inside the pores. It means that you had oxygen and the oxygen is no longer in the structure, so it's much more complex. Now this is very interesting. So in these previous microstructures that I showed you, Marcin had made our samples with one disk. Later on, when Marcin was trying to upscale the production of tetrahedrite, he started to make 3 and more disks in the same well and more than 3 disks. So it's 4 holes and each hole with 3 disks or something like this, if I'm not mistaken. And if you look at the structure, you see all these little things, these are pores. It's completely porous. The pores are really, really small. Again, 2 to 4, 5 nanometers. Again, according to the theory, this should not be okay. It should be bad. But we have quite good ZTs, again. So the question is, if we close the pores, how good is tetrahedrite going to be? So this is what we want to do. So in this case, we have zinc. So in this case, we had nickel. Zinc, the same, full of pores. It's much smaller. We don't really know the reason why they're much smaller, but it has to do with probably with the thermal inertia of the die, the graphite die, which is now much bigger because we have 4 holes and 3 samples in 3 disks in each hole. And it's sintering in a different way. Again, that's where we got the best values of ZT. This is a completely different porosity. So of course it depends also on the composition, but this is the chosen material. Again, the ZT is quite nice, 1.16, but again, multiple disks. So the question was this only us? Are we doing something wrong? Is Genicore machine different from all the other SPS machines? If you go to the literature, people don't show microstructures. If they show, they don't prepare. There's no metallography. They just crack the samples and observe the fracture surfaces, but then you don't see. I mean, you see the pores, but it's not really easy to see. But there is this paper by Balazs and Balazs, and they see exactly the same. That's the only microstructure that we could find. The rest, it's either SEM pictures with a very low magnification. You can see here the pores, but if you go to other papers, you don't really, it's too low. Sometimes they even have 100 microns here, so you don't see the pores. But in this case, they got something very similar. And there are many other papers where you can hint. You can see that the pores are there. It's just that they are not well prepared. Then we also see oxygen. So in this case, we had 50% synthetic, 50% mineral. These things here are iron oxide. These big things in the microstructure, in the SEM microstructures, are iron oxide. But if you zoom in here, what you see is this. So it's full of pores again. And if you zoom here between the little pores, what you see is this very strange contrast. And if you do EDS, you see that what you have is iron and oxygen. And now this is in the structure of tetrahedrite. Because this is just the same crystal. You're seeing in projection, this is TM. It's the same crystal. And what you're seeing is that there is a difference here. You have not so much iron and oxygen. And here you have more iron and oxygen, and also copper. So it's much more complex, and we need some sort of a metallurgical way of looking at this problem, because otherwise, if we don't really go deep into the microstructures, we don't understand what's going on in terms of thermoelectric properties. Now I'm going to present the last case study. So one of the things we were afraid of was the thermal stability of tetrahedrite because of sulfur sublimating. So we decided to see if we would replace with copper with any of those metals, and especially the ones which we thought could passivate the surface, maybe we could get the sulfur to stay inside. Very interestingly, if you look at the common valence of the atoms, you see that these ones tend to be ions which much more, it's +5, +6. Those we never managed to put inside the structure. They just precipitate out. They don't stay, even with mechanical alloying with a very high energy. We even broke our mill because we decided to really go for the highest energy possible, and we broke it. It's impossible to get chromium into the structure. But if you go to the papers, there's a lot of papers saying tetrahedrite doped with chromium. But if you look to the microstructure, you see that chromium doesn't stay in, not at these concentrations. And then what did we do? Okay, let's study the thermal stability. So we just crushed. I mean, the material comes from the mill. It's a synthetic material. Comes from the high energy mill, lab scale. And then we just put it in the crucible, and then we heat it up in air. 350 degrees in air for a day. And this is the mass that the powder gained. Of course, we're talking about powders. We're not talking about parts or legs. So this gives you an indication of the stability of the material. But this is a very bad case. I mean, the material will not behave like this if it's a part. This is just in powder form. And then we studied how the powders oxidized. And you see that here is mostly copper sulfide, and here it's tetrahedrite and fermatinite. This is undoped. Then you see that with the doped material you get a much better, it doesn't gain so much mass so fast, so it's not oxidizing. We could see that these ones we could not incorporate into the structure. You see niobium, for instance. You see that it doesn't go in. It just stays as little pieces. And these were the ones that we could fully dissolve. You could see that the best results, chromium didn't dissolve. It dissolved a little, of course, but most of it didn't stay, not in the fraction of replacing one atom. So this needs to be studied. How much chromium can we put inside? It seems to be beneficial. But when people say they put one chromium, they are not inserting one chromium atom into the structure. That's not possible. But you can see that it's quite stable, chromium and zinc and nickel. When you put iron, then it becomes worse. And in this case here, you see iron zinc, which is our composition. It's somewhere in between. So we tried to see, okay, if we have a lot of iron in our mineral, can we combine iron with other things? Zinc is good. Can we, for example, substitute one copper atom with chromium, but also add iron or nickel, and also add iron? And in this case, we are trying to add more than. But the conclusion was that it wasn't really And here it's a little bit better in terms of stability. We didn't test it for thermoelectric properties, but they are probably worse. And the others didn't seem to make too much of a difference. And these are the last results that I didn't show to anybody yet. But last week, we decided to crush some bismuth telluride powder, and just to see whether bismuth telluride would be more stable, much more stable than tetrahedrite, and it isn't. Of course, you need to see that this is the composition we chose, but you need to remember that this is the undoped, this is the composition we chose. I mean, the scale isn't the same. I just wanted to show you this, like this. So if you put a leg inside the crucible, you see that under oxygen, it doesn't really oxidize. But if you crush it, then it oxidizes a little, bismuth telluride. But it's comparable to what we see with tetrahedrites. So tetrahedrites, in the beginning, we thought they were not very good because they were sublimating the sulfur and pores and so on. In fact, with bismuth telluride at 350, we get the same type of behavior. So it means, I mean, this benchmarking is nice because it gives us some confidence that maybe tetrahedrite is a system in which we should invest. The important thing is really to close the pores, because without closing the pores, we don't understand the intrinsic behavior of the thermoelectric. And we are expecting to be better because the pores should be bad. So now the final slides, the thermoelectric benchmarking of tetrahedrites. So in this case, we have 20% mineral from Germany. So the ones which we could only get from collections. We couldn't have access to the mines. So we didn't invest in these materials, but we did some measurements, and you see that the ZTs are quite nice. We have in orange, in black, we have the undoped material, and the others are just synthetic and doped mixed with mineral. And in this case, 20%. And you see that we have around 1, depending on the sample. In this case, it's from Slovakia, 35%. And again, we get quite interesting properties. We are comparing with undoped, which is the black one. And it seems we get better performance with better than undoped. And this is the material in which there is, so these ones were sintered by Genicor with 1 disc, and these ones have been sintered by Genicor with multiple discs. So we believe that there is something, the thermal inertia of the dye, which takes much longer to cool down, that there is something going on. The pores are much smaller. We need to probably do much more, study this much more with all the parameters to be able to understand what's going on. But again, what we see is that with industrial upscale, we get even better properties than, we don't fully understand it, we have some hints, but it seems that we are in the good direction. So now I'm finishing. So what we can conclude is that it's very consistent, the data that we find in the literature. Iron alone is bad, but there is a synergy effect with zinc. We have produced tetrahedrites with very good ZT values, so we are confident in the materials. Nickel and zinc have been identified as potential stabilizers, so it might be that iron and zinc are what we want, but maybe we want to add a little bit of nickel or a little bit of zinc, or maybe even a little bit of chromium, depends on how much we can dissolve, because that stabilizes in terms of temperatures. The sintering parameters are key to the thermoelectric behavior, and this needs to be investigated further. But the most important conclusion is that the effect of doping is quite complex and masked by the processing effects. The porosity, which results from gas formation, is unlikely to be beneficial, because this is what you find in the literature in terms of tetrahedrite mean-free path, the phonons in tetrahedrite. And we are now doing HIP. So we're going to close these pores and measure. That's the last thing we're going to do experimentally. And the main conclusion is that these materials seem to be promising and worth further investing. Okay, thank you.
Thank you very much, Patricia, for this insightful and interesting.
Sorry.
Yeah.
Flip asked me if I could take it slowly.
So there is a question from her.
In the early part of the presentation, you indicate that excessive copper might lead to high ZT. So where does this excessive copper end up in the structure?
Knows. There's nothing.
Interstitial sites?
No, yeah, it's probably interstitial, and they say it forms this glass behavior. So it's, and also that it's a liquid kind of behavior, because the copper ions are mobile.
This is very interesting. It reminds me the zinc and timonite. You know, one phase. That's strategically stoichiometry. But zinc and timonite, 4-3 phase. They have a lot of interstitial side of zinc, which also mobilize and decrease the thermal conductivity.
Yeah.
But then the dark side, the drawback is it might participate at elevated temperature.
Yeah.
It could be very comparable in this case.
Yeah.
Very interesting investigation.
Yeah, and zinc is always interesting as well, sublimates and so on. There's a lot of things. It's very complex. These materials need to be studied. I mean, if you think about for other silicon and these other types of semiconductors, I mean, here we're just putting a lot of, another important thing I didn't mention, but when you produce things by mechanical alloying, you're always putting about 1% of iron, maybe 0.5 weight percent of iron. But iron is not a good thing. Or maybe it is if you combine with other things, but nobody knows. We need to study this.
Yes, okay. Any other questions? So thank you very much, Patricia, for this nice recap of the characterization and microstructure. It will give a good insight for the application. Now we will move to the applications from industry. We will have two talks at mid temperature range and low temperature range in the two following talks. So we will start with Anir from Thermagy, and we will follow up with Hao from technology on this part of the session. So the floor is yours, Annie.
Perfect. Thank you, Amin. So good afternoon. In my talk, I will be focusing on the mid-temperature thermoelectric devices. And here we are incorporating the tetrahedrites that were elaborated upon in the previous work packages into an actual thermoelectric device. First, a brief introduction about our company. So we were formerly called RGS, which is also the acronym for the type of process we had patented to make our materials. So that was the ribbon growth on substrate method that was developed at the TNO-ECN, which is the Energy Center of the Netherlands. And since then, we initially focused on silicon-based materials for solar photovoltaic devices. But in 2020, we pivoted towards thermoelectric generator devices. So there we were using silicon germanium. Those are high-temperature thermoelectric materials that can convert a delta T of 800, 900 degrees centigrade into power. And since then, we have been focusing also in system integration, which I will elaborate a bit on as we go forward. So at Thermagy, we have two main application scenarios. One is the space applications, which is what our production methodology has been qualified for. And then the second one is for terrestrial applications, which is where we are also developing the start module for. I will briefly touch upon the space applications to show you also the perspective and the applications where thermoelectrics have been quite successful. Here, maybe some of you know about radioisotope power systems, which have powered quite a few of these deep space satellites, which have also left our solar system. And these kind of systems have varied from 10, 50 watts of electric going up to hundreds of watts of electric, depending on the needs for that particular system. And now, increasingly, they're also looking at alternate isotopes. So in these kind of systems, what you're converting is a radioisotope, the decay heat from that into electric power to supply power to your rovers, as well as your probes, which are powering the deep space satellites. So it has to be a flexible system, and this is also what we have been doing within Thermogy, looking at modulating our architecture to fit to alternate isotopes and heat flux densities. One of the main driving applications recently has been the quest to get to the moon. So now I think you must have seen the recent Artemis mission again, where from NASA they're pushing, we need to get people back onto the moon, especially to explore the south lunar pole, where they have discovered water which can be used for habitats in the future. And yeah, there have been many missions from various agencies, from NASA, from also proposed new missions from ESA as well as ISRO in India. And when you want to go to these permanently shadowed places, like where minerals as well as water can be found, you cannot power it with solar cells because it's permanently shadowed. There are the long lunar nights also, which is 14 days without any sunshine. And that is where radioisotope power systems based on thermoelectrics can play a pivotal role. That has been the main focus within our company, where we are developing these high temperature thermoelectric devices. While for the terrestrial applications, we are focusing more on the mid temperature. And this is what we have seen based on a lot of literature, that there is quite a bit of waste heat in heavy industry. So up to 123 terawatt hours of waste heat is available at 500 degrees centigrade, depending on the final end use. And the EU is requiring a lot of these heavy industries to start pivoting towards renewable energy use each year. So they need to increase that more and more. The second key application that we are looking at is the combined heat and power. So there we want to integrate our thermoelectric devices in the hot zone of the boilers. So these boilers are for burning wooden chips to power homes. And then if you are able to channel that heat into the thermoelectric generator, you can also get electricity out of it. And this was the application which we selected within the START project as a driving requirement setting for our module architecture. This is to give you a snapshot of our most mature high temperature thermoelectric generator device. What we work on is first a unit, a 100 by 40 millimeter unit, which we called a module. And then we also look at systems where we are able to string together up to 15 modules of such modules. And this is an entire panel of thermoelectric devices which can generate up to 100 to 200 watts of electric. So that's serious power, especially in combined heat and power applications. So this is a bit of a recap of what I had shown already in the previous workshop, where explaining when you're modeling a thermoelectric unicouple in a device, there are many aspects that you have to take into account. There's not only the material properties that Patricia touched upon, so the temperature-dependent thermoelectric properties such as Seebeck, electrical conductivity, thermal conductivity, but also the mechanical properties, because these devices have to actually go into something, right? Are you going to conductively couple it? Then the hardness has to be robust enough that it can survive that kind of conductive coupling, as well as fracture toughness is a key aspect that we have to take into account. So these are properties that we measure for all our materials, be it for high temperature or for the mid temperature materials. Besides the material properties, there's also the interfaces. So these are the thermoelectric materials, and then they're connected on the cold side and the hot side. So the interfaces have to match the coefficient of thermal expansion between the active material and the hot and the cold shoes. So that's something we optimize within the START project also to make sure that is possible to do, as well as the electrical resistances have to be low enough. So that's the bonding method, right? What kind of bonding material do you use? and the diffusion barrier layers in between. So depending upon what your contact resistances are, it can make a big difference in your final efficiency. So you can model a perfect material, a perfect bonding, but then if your resistances at the interface is high, that can drop it down quite a lot. The third aspect is the thermal interfacing. So here you have the heat coming in, and then you have to also pull out the heat. So we have to effectively choose what kind of coupling do we want to do. For our high temperature silicon germanium based thermoelectrics, where we are operating at 800, 900 degrees centigrade, typically we are focused on radiative heat transfer. Now, when you want to also get as much heat in as possible, we also do more convective and conductive. This is what we are focusing on in the start module. Similarly, on the cold side, you have to make a choice about whether you use convective heat transfer through forced airflow or cooling water itself, which can also be used as a way of recovering the heat that was going through the thermoelectric device itself. As I mentioned to you, the combined heat and power application, the idea is that if you have heat going through, you get electric power, but you can also use the heat which is in the water itself. So that's to maximize the round trip efficiency of such a device incorporated into a system itself. So this entire simulation package, as well as the manufacturing, is what we have optimized within Thermogy, which we do for our high temperature materials, the silicon germanium based devices. And you can see the entire downstream processing where we melt, cast, we do polishing and dicing in-house. We also optimize the bonding methods as well as set up testing platforms for such devices. This is just long-term test, which is up to 10,000 hours for our Thermogy silicon germanium based devices. So you can see that this device was able to survive up to 700 degrees centigrade on the hot side, generating up to 2,000 watt per meter square. So that's quite high. We also exposed it to 100 hours of up to 900 to 1,000 degrees centigrade on the hot side. When we had internally tested it, we also went outside. We carried out what we call lighthouse projects. So these are entire panels of our silicon germanium modules that you see here that was exposed onto steel slabs, which were flying by in various environments. So Tata Steel, with silicon manufacturing, as well as other steel manufacturers. And here we were able to show that this is a robust device that can generate electricity, and we can also supply heat at the back of our device. So here you see a plot of the hot side temperatures, the heat flux densities, and the electrical power densities that you get out of such a probe. So what you can identify is that the silicon germanium works quite well from 600 degrees centigrade up to 900 degrees centigrade. Below that, we need another solution. And this was our main motivation to also look at the tetrahedrite materials within the START project. So identifying that challenge, we saw that there were many applications which leads to a hot side temperature of 400 to 450 degrees centigrade. And when we look in the market, there are two main stable material classes. There is the high temperature silicon germanium, which is stable in air, up to 900 degrees centigrade. And then there is a low temperature bismuth telluride, which Patricia showed is not stable at 350, but up to 200 degrees centigrade, it is the main module which is still used. So the mid temperature, there have been many reports of various materials, but limited stability studies. And that is something that motivated us to look at tetrahedrites, especially coupled for requirements for combined heat and power applications. So we chose that, and then we defined the requirements of such a device. This slide is a recap of what Philippe already showed. We are looking at, we source the P-type tetrahedrite material from waste sulfide mine dumps and tailing. And we first focused on synthetic materials before combining it along with the mixed mined and synthetic in the START project. And in work package 5, which we were leading, Thermogy was leading this work package 5, the first activity was setting up the model of this entire unicouple. We did the first analytical simulation where we chose tetrahedrite as one of the main materials of the p-type and went through a series of alternate n-type materials. And here we wanted to see what the sizing of the pellets need to be to couple to the combined heat and power application. So the heat flux density was defined, and then we did the sizing of the pellets themselves. So that was first done analytically, and then we transferred that into a COMSOL model that we built, and also along with SINTEF optimized, where we optimized the fill factor for such a unicouple where it peaks at a certain value, so that's per unicouple. And we also looked at what would be the expected power densities, given ideal conditions where you have good resistances at the interfaces. So this was the thermoelectric simulation. Then we also did the FEM stress analysis. So we wanted to see when you couple different materials, so ceramic substrates with the electrodes and the materials, where do you get the stress concentrations? So that's something also we wanted to relieve in our module. Since it's not the same material class. You have a tetrahedrite p-type, but you don't have a tetrahedrite n-type. So in the project, we chose an alternate magnesium-based n-type material with a very different coefficient of thermal expansion. So that plays a key role, and that's something that we had to adapt for in the module itself. After the simulation was performed, we sourced the disk, as Marcin was showing, from GenieCore in the optimum pellet architecture, where we are able to cut them in the sizes which we had got out of our model. But before dicing them out, we also coated them with 2 layers. One, a diffusion barrier layer, and another layer on top of it to enable the bonding with the ceramic substrates. So here you can see the pellets which were obtained. So eventually we were able to optimize the roughness to a suitable degree that we are able to get a coating which does not break away. And here you can see the coating mass was quite uniform between all the pellets. And these pellets were then put together into the next architecture. Here you can just see snapshots of where we defined what the architecture of a 45 by 45 millimeter square module was. And we designed the ceramic substrates with the electrodes and also optimized the bonding for the pellets themselves. So we did that first on the unicouple level, and then we upscaled it to the entire 45 by 45 millimeter square module. Here you can see it's 31 couple module with 62 pellets. So here, Ambien worked on the milling of the material. So they break it down into almost nanostructured, microstructured powders. Then GenieCore worked on sintering the discs, and the discs really had to be controlled for thicknesses because that's what's needed for our module itself. The pellets have to be the right thickness so that we can bond them in the unicouple. And then once we had characterized the materials along with Patricia and Philippe, we could optimally expect what the powers would be at the unicouple level. So we diced the pellets. We had designed the architecture, and then we bonded the entire module at once. So that went quite successfully. So in the last 2 weeks, actually, so just the last week, we made the first module with the tetrahedrite incorporated material. So that's the tetrahedrite on the p-type, and the magnesium-based material on the n-type. So here you see the 62 pellet module, where we started carrying out thermoelectric characterization. So we have a test system where we are able to conductively couple it and then start heating it up. Here you see the hot side temperatures of our TEG module. So this is on top of the ceramic substrate. So at the top of the pellet, it is slightly lower. But our intention is to extend the stable and to go to even higher temperatures if possible. One key aspect to note is that the internal resistance of the entire module is quite low. It is 1 ohm. And this number matches quite well to what we had measured at the individual pellet level. So that shows that the bonds have come out quite successfully. And we are not adding a lot of resistance at the bonding. So this is reflective of the pellet resistances when they're added up. So here you see, we are able to generate 1 watt for now at a T hot of 250 degrees centigrade. So that's quite exciting that this module works. It has survived. It has come out of the testing system without breaking. So that's also good. We can continue testing till the end of the project. And it's a key output of the start project itself. So a few takeaways. As we mentioned, at Thermogy, we make conversion technologies that are fit to various heat flux densities. We can simulate and manufacture materials as they are needed. In the high temperature, we work with silicon germanium materials. In the mid temperature, which is where the terrestrial applications lie, and there we are working on selecting a key mature, stable material. And the start project gave a lot of feedback on which material class could be used for these applications. With that, I would like to thank you for your attention and looking forward to questions.
Thank you, Annie. Any questions? No? Yes.
Thank you very much. Do you have already an idea of the efficiency of your module?
Not yet. So that's something we'll have to back calculate from the heat going into the water. So that's something we'll have to look at. So for now, we have the temperature measurements and the powers. Yeah. So that's ongoing. Yes.
Okay, thank you. And do you have any special protective coating,
No.
especially for the magnesium-based material?
No. So we had done some coating analysis beforehand at the material level, and eventually we saw that you form this oxide layer regardless. And that's something that we have noticed, that it might also not be as harmful at the end, that it could also be its own coating. Yeah. So eventually we decided to simplify that and just use it in air. Yeah.
Okay, thank you.
Merci, Geoffroy. So we will move. Thank you very much again, Anir, for your talk, and then we'll welcome Hao Yin from Technology to present the second part of the applications on the low temperature range modules and devices. So the floor is yours.
Hello, everyone. Glad to be here. I would like to start with one of the first kickoff meeting that we had with START. That was 4 years ago almost. That we took the opportunity to bring the whole team of technology as a team building in Lisbon. You can see the happy faces with the pina colada in the hands, and also with this little tram. What I want to say is time flies. We are very glad to be part of the START family, which witnessed the growth of the company. At that time, we have, well, not all of them are full-time. We have 4 or 5, and now we're 12 people in the company. It's really a journey. Let me remind you what technology is doing. So we started with patents of material based on zinc and timonite. And then we realized the biggest problem for commercialization of thermoelectric is not a single fact. It's a fact of a chain. We're lack of good materials, we're lack of the stable materials, we're lack of the module, we're lack of the application. And they come hand in hand. Without a good material, without a stable module, we cannot find a good application. And vice versa, without the application, without the strong demand from the application, we don't have enough resources to develop the material. So we've decided to bring whatever is available at the time, to build them into products, and to show that despite we know that we need to find new materials, but we can have some benefits of using thermoelectrics. And that gave birth to a series of products. They are industrial available, commercially available products all of them are self-powered. For example, these small ones that have been sold to more than 10 countries in the world. So what they do is it uses the surface heat from pipelines or from machines to power itself and to measure the temperature, give the signal, or even send the data by wireless. Right? It fits the demand of this digitalization, IoT, where you don't need to install the cable or use the batteries. It is also very well suited for underground pipelines, for district heating, oil and gas, where it's difficult to install battery, or it's just too dangerous to use batteries. And by definition, when we work with application, our main contribution comes at the later half of the project, because we expect to implement the new material that developed in the project, and also we try to build that into a product. So even though in the project administrative point of view, we try to avoid this hockey stick growth, right? We try to not wait until the last minute to do what we want. So while we waiting for the development to happen, we also actively involved in the discussion and also share our early days, the expertise that we accumulated in the early days. For example, this stacking the the sintering process, and also the deposition of the layer, the barrier layer and the conduction layer, which I'm very happy to see that has been adopted by some of our partners in the consortium. But last but not least, this hockey stick actually happened. So we managed to make a large flex stack, which I also have here. I'm pretty sure that we can claim this is the world's largest single TG. And this is not limited by anything, so we can make them even bigger or even unlimited. We produce them continuously and then cut it after demand. So this I'm showing is a demo. And we have the real one, the real working one in the box. You can see it, but please don't touch because it's very vulnerable. It's the only one that we managed to make. The challenge is we don't even have the facility to characterize this. You know, we're working on it. But how do we distribute the heat evenly on one side and cool it on the other? We don't know yet. We're building something. The reason that we want to build it in this format is, as I mentioned, technology works on large-scale industrial waste heat, especially low-grade waste heat. That means the temperature difference, the delta T, used to be small. And in order to get significant power output, we need to implement in very large scale. When we talk about scale, we're not talking about square millimeters. We're talking about square meters, even tens or hundreds of square meters. For example, covering an annealing oven, which is 2 by 2 meters and 100 meters long, or a chimney, where we have the flue gas. So in this scale, we cannot implement the small TGs that we used to see. No matter what, it will be too expensive. And that also leads to how do we manufacture those modules? If you're going to cut these legs, you know, a few millimeters in footprint, it's going to be too costly, because cutting is a linear process. In order to get more legs, you need to buy more machines. There's no, you cannot just do this exponential growth of the capacity. And by doing this, we use the pellets directly from sintering, and then we do the deposition of the layers, and then we build them into modules. We actually need this big footprint, because as mentioned, when we cover huge areas, in order to build up the voltage, the current is going to be very high. even though the delta T is small. So we need the legs to run bigger currents. And that's why they end up in this way. And here is also a summary of how these modules are built. You're familiar with some of the processes that MAN is the expert, and we got the pallets from Genicore. This is also how we produce the pallets in a stacked manner. This is how we do the polishing and grinding by 2 layers. We need to polish them down to the same height, and also with a specific surface smoothness or roughness. This is how they look after grinding, and then we do the coating, deposition, before we put them into the modules. And this is how we do, very recently we got tetrahedrite and magnesium antimonide. So these are real material that we build into this, and then you will look at it in a box. So this is the first attempt to sort of get some output. You can see it's very homemade. We have a grill oven, and then we put a lot of heat sinks on top of it. This is very rough. There's no control of the temperature distribution at all. And then, of course, we get a ridiculously low output because they are canceling each other. So it's not a proper way of doing it. But the internal resistance of this big module, that's below 1 ohm. So it actually works. That is a very brief summary. And I would say it's a good closing of our contribution in START. And of course, we will keep working on this path. Thank you.
Thanks very much, Hao. Are there any questions? No? It was so clear. Okay. So this was our last presentation on the application and devices. So now we have half an hour coffee break. Thank you very much.